Hi everyone, I'm here at New York University today to talk to Professor Matt Kleban of the Department of Physics about the multiverse. Matt, can you tell me what the multiverse is?
So people mean a lot of different things by that term, and I've never liked it that much actually, because for me, universe is by definition everything there is, and so doesn't really make much sense. But the way a lot of people mean that is just to say that the part of the universe we can see is a lot smaller than the whole thing. And the reason that might be the case is we're limited in what we can see by what's called a horizon. So when we look through the most powerful telescopes that we have, we look as far as we can, there's a limit to how far we can see. We can see tens of billions of light years, the distance that light travels in tens of billions of years. And beyond that, the universe becomes opaque.
Yeah.
Not because at this time it becomes opaque, but because far in the past, the universe was like the inside of the sun. And the inside of the sun is opaque. If you beam a laser pointer at the sun, it doesn't come out the other side. The whole universe was like that if you go far enough back. And when you look far away, you're looking back in time. You're seeing the universe as it was when light was emitted from it back then, that distance. So there's a horizon that limits how far we can see, and we just don't know much about what's beyond it. So there's no reason to think that what we're seeing is the whole universe any more than if you stand on a hill and look around, what you're seeing is the whole Earth. And so most people think that there is a larger universe out there. When you talk about the multiverse, you're saying that the larger universe that's out there is very different from the part we're seeing. So again, if you're standing on this hill and you see, I don't know, a plain around you, maybe with some pine trees or something, it doesn't mean that the entire Earth is a plain covered with pine trees. There can be lots of variety. And so that's the most sort of basic notion of the multiverse.
So basically, just to repeat, so you have what we can see of our universe, which may continue, even though we don't have access to that, just because we can't see beyond the horizon. But then there could be other things out there which are not this bubble that we call the universe, right? That's what you mean.
Yeah, so in a lot of theories in physics, there are multiple phases. So you can have the same substance fundamentally, which looks very different and has very different properties. For instance, dihydrogen oxide can be water, can be ice, can be water vapor, and those three phases are very different from each other. So a lot of what we think might be fundamental theories of physics predict that there are phases of the laws of physics almost, that the particles we're made of, for instance, might not exist or might have very different properties if we were in a different phase, and that those phases can exist. And they probably do exist somewhere in the universe. So if you were to go far enough in a straight line, you'd eventually come to a part of the universe where the particles have very different properties, and those can be very exotic, those phases. You can have different numbers of large dimensions even, because in some of these theories there's more than the 3 dimensions of space that we're used to. And some of those extra ones that we think they're maybe there, but they're too small for us to see, they might actually be large enough that you could take a walk in them. Only you wouldn't be able to take a walk in them because the stuff you're made of doesn't exist over there. So these phases can be very exotic, very different from what we see around us.
And how does that go? I mean, how do you get those phases? Because that sounds like what you talk about is you have fundamental constants of nature that may vary from one phase to another phase, mm-hmm. right? And hence you have different properties. So what sort of theory can generate this kind of stuff?
There's a variety of different theories that can predict this. String theory is maybe the most prominent, and that's where a lot of these ideas came from in the first place. And the reason you have all these phases in string theory is actually because of the extra dimensions. So string theory has this mathematical peculiarity that it predicts that there have to be 9 space dimensions in one time. And since we don't see 9 space dimensions, we see 3, we've got to hide 6 of them somehow. And there's a way to do that, which it's called compactification. Essentially, if those 6 dimensions are curled up, if they're small enough, then everything that we're used to, including ourselves, fills those dimensions uniformly. And in that case, you don't even notice they're there. And to detect them requires an experiment that can probe very, very short length scales, about the size of these dimensions. But depending on, there's many choices you make when you compactify these dimensions, and depending on how you do it, you get different laws of physics at larger distance scales. In other words, if you don't have access to this very powerful microscope that can see down and see those dimensions, if you don't have that, then the physics to you looks very different depending on precisely how those dimensions are curled up. So that's one origin of these kinds of phases. There are others. You can get this in more conventional theories called quantum field theories. And then multiple phases is, again, actually pretty generic. One thing about string theory, though, is it predicts there's a huge number of different phases, a very large number.
Can you tell us about this? So basically you're saying that you can sort of twist and poke those extra dimensions, and those different geometries of the extra dimensions will generate different physics in the ordinary 3 dimensions, right? So that's the compactification idea.
That's right.
So this thing has a name, right? This is the landscape.
Yeah, the landscape of string theory, that's right, yeah.
And so what's the story about the many, many different possible spots on this landscape? How does that work?
Well, 6 isn't a very big number, but these are 6 dimensions. And so when we talk about the number of phases in the landscape, it has to do with a number of different ways that you can take 6 dimensions and curl them up. And it just turns out, because of some kind of combinatorics, possibilities multiplying other possibilities, that very rapidly, as the number of extra dimensions increases, the number of possible phases increases as well. And with 6, it's easy to get numbers like 10 to the 100 or 10 to the 500, so that's a 1 with 100 zeros after it, or 1 with 500 zeros after it phases. And there's an interesting, if you want, I can talk about the cosmological constant problem and why this number is relevant.
At some point, yeah, we'll get there.
Okay.
So one thing about this is that to say there are 10 to 500, right, possibilities, it's in a sense saying that they're all possible or realizable, right? So is this number just counting the possibilities and saying they're all, in principle, they could be realizable in this landscape? There's no selection process that would favor some more than others. Is that?
It's saying, well, there might be it depends on what you mean by favor. So if you ask, what are you likely to observe?
Well, no, I mean, when you talk about different phases of matter at a certain temperature, you know that at a certain temperature, water is going to be the favored, the phase of H2O, and at different temperatures it won't be. Water meaning liquid water. So I wonder if there is something equivalent in these in these possible other universes, so that some may be more energetically favored than others, and if that kind of thinking even makes sense.
Yeah, no, it certainly makes sense. In the very early universe, we think the energy densities and the temperatures were extremely high. And at extremely high temperatures, all of these phases are, it's not the right way to think about it. It's like when you heat up H2O enough, you have just water molecules flying around. And in a sense, this is like water vapor. But once you let it cool down, it may remain water vapor depending on how cold you make it and what the pressure is. It may become liquid water, it may become ice. So in the early universe, all these phases are sort of coexisting, and they haven't really differentiated themselves yet. And then as the universe expands and cools, different parts of the universe will find themselves, just by coincidence, in different phases. So not only are these possibilities there as possibilities, as possible phases that could exist, there's no reason to think that they don't exist. In fact, there's very good reasons to think that they must exist somewhere. Quantum mechanics, among other things, makes it really hard to forbid any possibility like that from being realized. If something is possible, it happens.
Right.
At least some of the time.
Yeah. And are those, but you can't travel around these phases, right? You can't go from one to another.
You certainly can't, because you're made out of particles that
Right.
don't exist over there. So if you tried to enter one of these phases, you'd either bounce off the wall that separates you from it or just be annihilated if you managed to get in.
So maybe you can explain to us something, so let's consider each phase a different universe, which is, that's the essential idea, right? That each one of these phases is a potential universe?
Well, let's just think about a large universe of which we can only see a small part. And in some parts of this universe, we're in one phase, like the part we're in the phase we know. But if we could somehow travel far enough in a particular direction, we would come into a region of the universe that's in a different phase. And there'd be a wall called a domain wall that separates our region from that other one. So that's what people mean by the multiverse some of the time, is this big universe with these different regions. But really, it's just a big universe with different regions.
So they're not, there's a term causally disconnected, right? Maybe you can tell us what that means and if these different phases are causally disconnected or not.
Right, so causally disconnected refers to the fact that nothing can move faster than light. And so if you have an event which is, let's say, very distant, and then you wait an amount of time that's less than the amount of time it would take light to propagate from that event to you, then whatever occurred at that event can't affect you in any way, because no signal from it will have reached you. So very distant parts of the universe are causally disconnected from ours, because whatever happened over there wouldn't have had time to reach us in the lifetime of the universe. And if the universe is very, very large, then most of it is causally disconnected from our region. However, there's no reason to think that all of the regions in which there are other phases must be that distant. So some of them certainly would be, but some of them might be causally connected to us. And in fact, we would even have a chance of seeing them. That's something I've worked on, and there are signals that you can look for in the cosmic microwave background, which would be indications that our region of the universe has collided with another universe, if you want, or another bubble of a different phase. You can make quantitative predictions from that. People are searching for it in data from satellites that observe the sky.
Okay, so let's go there, because that's super important, right? So maybe you can explain all that again in a more sort of slower, So and maybe the question I'm going to ask is, okay, so you have these possible phases out there of the multiverse, right? And the question is, could we ever know they exist? Are they physically, they are mathematically plausible, but they are physically falsifiable, meaning can you have any idea, that they are really there or not?
Yeah, so my contention is that we can receive signals from them, which would prove beyond any reasonable doubt that there are, in fact, other phases, that there is a multiverse of this sort. And furthermore, that we could make a different sort of detection that would falsify the idea that there are other regions of our universe, at least within the class of multiverses that most people have been working. So I think this idea is both predictive and falsifiable. Predictive in the sense that it predicts signals that can't be produced by any other mechanism we know
Are
of.
you sure of that, though? Because that's a very strong claim.
Yeah, I mean, I'm sure of it within the class of multiverses that I understand. Now, again, this term multiverse is a slippery one. People mean different things by it. So I would say...
No, I mean, so basically you're saying that telling a story, right? One time, a long time ago, nearby universe, or whatever you want to call it, phase, sort of grazed by ours and sort of collided in a very soft way, I imagine, because otherwise we wouldn't be here. And that would leave some imprint in our universe that we could see in the cosmic microwave background.
Yeah, so it's let's discuss the collision. So when these phases can be there starting from the very early universe, because just coincidentally that part of the universe ended up in that phase. That's one way they can form. But another way they can form is by what's called a first order phase transition, where a bubble of a new phase will form inside an old one. Typically this is when the old phase has higher energy than the new one, and nature prefers to lower the energy, so a bubble of this new phase can appear surrounded by a domain wall, the boundary between the new phase and the old, and then this domain wall will expand because it's energetically favorable for it to do so. And because we haven't talked about inflation, but these phases tend to expand very rapidly. So they don't usually disappear. Once there's a part of the universe that's in some phase, it reproduces itself faster than it can decay by this bubble formation. So we believe that the universe is really large. Most of it is full of these rapidly expanding phases. The part we live in formed from one of these phase transitions. So we're inside a bubble that appeared as a result of one of these phase transitions. If so, other phase transitions are occurring, other bubbles are being formed, and most of those are causally disconnected from us. But occasionally one is going to be close enough that it will collide with ours. It's not really a glancing collision because both bubbles are expanding at about the speed of light, so they smack into each other full on. One might be larger than the other, but they collide full on. And then there's a domain wall that forms that separates those two phases. So there's a domain wall that separates each bubble from the parent phase. but once they've collided, there's a domain wall that separates the two from each other.
Okay.
That domain wall has dynamics that depend on the energies, the vacuum energy in these two phases, as well as some other factors. But typically, if one of the phases has very low vacuum energy, as we know ours does from observation, the domain wall will be repelled from it because the other phase has higher energy, and the domain wall will want to move into the higher energy phase for the same reason, that it wants to lower the energy of the whole system. So the domain wall will accelerate away from us, which is a good thing, because if it accelerated into our phase, it would very rapidly be moving at nearly the speed of light, and then it would annihilate everything in its path. The only good news is you wouldn't know it was coming by the time it went from your toes to your head. Nerve impulse would never have had a time to propagate. So you would never know it was coming, and you'd just wink out of existence. But it seems that having very small value of the vacuum energy is actually a protection against that. So in that sort of a collision, the domain wall is not a threat to us because it moves away. But the collision in the first place, and just the formation of this wall, injects a wave of energy, and it's a very, very large wave of energy. It's a huge perturbation in the early universe.
How does this energy go from the wall into us, into the inside?
So the physics of these phases is intertwined with all of the physics inside our bubble. And in particular, it's intertwined with the physics of the very early universe. There's something called inflation, which happens after our bubble forms. And well, we don't know for sure that there's a multiverse. We're pretty sure that there was inflation in the early universe. The field that causes inflation to happen is connected to, it's different in these different phases. And so it's affected by this domain wall because it has different physics on the other side of the domain wall. It doesn't exist on the other side. So the domain wall gives a kind of it creates a wave in this field called the inflaton. So that's the initial effect. But that translates into a wave in the plasma. So I said the early universe is like the inside of the sun. Yeah. The sun has seismic waves propagating through it. It has currents, it has solar flares, it has lots of dynamics. The early universe can have sound waves, essentially, waves of this plasma. In the end, the effect of these collisions is to produce a pattern in the distribution of stars and galaxies we can see on the largest scales through the biggest telescopes we have today, and also in something called the cosmic microwave background, which is this ancient light left over from the early universe. So it's a big effect initially, but by now it's very diluted because the universe has grown by such a huge, it's grown so much larger than it was initially. So it's like a tidal wave, but then gradually dissipates as the universe grows.
Right. So the two questions that people tend to ask about this, one is, have you found anything, or are people looking, and what's the story so far on this?
Mm-hmm. Right. So this is all very new. The first predictions for what these signals would look like were made less than 10 years ago by me and other people here at NYU. And there have been a number of searches for these signals in data from satellite observatories. Some of those searches seem to find significant evidence, and others did not. So I would say the situation is there's probably no evidence for any signal. More data is coming. One of the effects of these collisions is to produce a pattern in the polarization of this cosmic microwave background light, and there's not to date been a high-quality map of the polarization released. So there is more information coming. Another effect is on large-scale structure, the structure of galaxies and stars, and there's constantly new information there. So we haven't seen it yet with any kind of certainty. It's possible that we still will. It's also possible that everything I'm saying is correct, and there were bubble collisions that we could have detected, but they're simply too faint for us to be able to see. And in that case, we might never know. We could easily live in a situation where all of this stuff is real, but we'll never be able to measure it for sure.
Right. Which is sort of an unpleasant situation in physics, right? Mm-hmm. I mean, how do you feel about that? That's more into the metaphysics of the whole stuff, mm-hmm. right? So maybe I'll hold on that one. But
sure.
So one important thing though is, okay, so let's say there is a signal that corresponds to your prediction, mm-hmm. which is some sort of ring-like structure in the microwave with this double wave-like thing, right?
That's in the polarization.
Right.
In the temperature, it's a disk that gets brighter near the middle.
It's a disk, right?
Yeah.
That makes sense.
Mm-hmm.
the problem with observations in physics usually is that they may point towards an effect that you say it's vindicating my idea, but there may be other sources that may be creating similar effects that may lead you into believing you're seeing something when you're not. So the question is, and this is super important, is like, have people thought of other possible processes that could generate similar signals in the microwave background, or is this really a very unique thing that's very hard to come up with in any other scenario?
Yeah, so there's two parts to that question. So the dominant theory of where the patterns that we see in the cosmic microwave background came from is this theory of inflation. And according to inflation, those patterns are random in a particular way. They're Gaussian random noise. So the first question you have to ask, given any kind of prediction, is how likely is it that Gaussian random fluctuations would mimic the pattern you're looking for? Right. And when people did these searches, that's what they were comparing to. They were comparing to the sort of fiducial theory, that the baseline theory, that everything in the CMB is random. And as I said, some people claim to find evidence for this, others said not. I don't think there's a strong case to be made that there's a signal there. So that was what they were comparing to. Now, had they detected something which was clearly not coming from random noise, then you should ask, is there a third theory, not bubble collisions and not random noise, but a third theory which could also predict a similar pattern? One problem, or it's not really a problem, but the nature of science is theories are kind of continuous. There's some space of theories. When you make an observation, you can shave away part of that space, but you're never left with one theory. There's never a unique theory that predicts anything. There's always some space of theories. For instance, there's not really a unique theory of these bubbles. There's parameters in there that can vary. There might be something more complicated, which is related to this, but it's not quite the same thing. So certainly there are other theories that could predict something similar. I don't know of anything that's any less radical than this proposal that could predict a signal like this, because these bubbles are enormous. They cover they cover a part of the sky which should have been causally disconnected, actually. So the reason that it's so hard to mimic this is there's nothing that could have happened in the universe since the end of inflation which could affect that much of the sky. So large scale, when you look at this direction versus this direction on the sky, and you're looking as far as you can see, you're looking at 2 points that were never in causal contact except in the very early universe. So if there's a correlation between them, that's not just this random fluctuation, but some coherent pattern like this, it had to have been produced in the very early universe before inflation began. Okay. And we don't have, I won't say there's absolutely nothing else that could have happened that could have done this, but I'm not aware of any other possibility.
And another thing which is interesting, at least to me, I don't know about the course, but another thing that is interesting is when you make these models, right, you talk about phase transition. I've done a ton of work on phase, as you probably know. So you are talking about bubble nucleation in different regions of the universe. So you're making a very, very important and I think strong assumption, which is that physics works in different places, so in a sense, you're moving away from our universe, but you're close enough that the physics is not too far away from what we're used to in terms of nucleation processes still happen, domain walls still form, and they propagate at the speed of light, which means there is a speed of light in that universe, which is a constant of nature in our universe.
Right.
So
that's true. So all of this, so when I said there are these phases that have very different laws of physics or low energy laws of physics, they all fit within one overarching fundamental theory that I'm assuming is there. Okay. If it's string theory, then we know what it is. It predicts the existence of these phases, and the speed of light is built into string theories. String theory is a Lorentz invariant theory, and so that's just built into it. I also mentioned quantum field theory, that this can have multiple phases, and again, in the structure of local relativistic quantum field theory is built in this limit on the speed of light. So there are certain things that are there. There are certain laws of physics which aren't just environmental, which don't just depend on which phase you're in, but which are really fundamental. Now, obviously, there could be something beyond that we don't know, or that could simply be the wrong picture. And indeed, we're assuming that it's the right picture, and trying to test it.
Yeah, no, that's great. Okay, so now let's move a little bit away from the physical picture, which will probably confuse a lot of people. But
sure. Yeah.
So let's move away from the physical picture, and let me ask a little bit about you mentioned you wanted to talk about the cosmological constant, and there is this whole issue of fine-tuning in the universe, which is a very big deal. So maybe you can tell us what is the fine-tuning problem, or if it is a problem, and how this sort of scenario can take care of it.
Right. So the cosmological constant problem is regarded, at least by some, as the biggest problem in theoretical physics today. What it boils down to is quantum mechanics predicts that empty space has an energy density to be precise, that there's an energy that's proportional to the volume. So if you have an empty can of vacuum, it's not really empty, it's got energy inside, and the energy is proportional to the volume of the can. When we compute how much energy that is, we get an enormous answer, a huge amount of energy. It's way more energy than there is in solid rock, let's say, much, much, much more. And of course, space doesn't have as much energy as solid rock, we know that for sure, because we can weigh it, basically, by observing how gravity is affecting the expansion of the universe. So in fact, we know that there is some form of energy in empty space. Well, when I say no, we have very strong evidence. This is called dark energy by cosmologists. There is a substantial amount of dark energy, but it's vastly less than the prediction of quantum mechanics. So why is it so much less? It turns out the prediction of quantum mechanics is hard to be precise about. It's easy to see that the energy density should be very large, but it could be large and positive, it could be large and negative, and by coincidence, it might happen that it's close to zero, as close to zero as what we measure. But the magnitude of that coincidence, it's a huge coincidence because the raw value that comes out of these calculations is so much bigger than the observed value. So when I say it's hard to calculate, it's because we don't understand physics beyond a certain length scale. That is, we have microscopes and then we have particle accelerators that let us see down to a certain scale, and we can calculate the vacuum energy, the contribution to the vacuum energy that comes from that range of physics. But at smaller length scales, we don't really know what's going on. That's where the uncertainty is coming from. And those are the ones that matter the most, actually, for this vacuum energy. So we're completely at the mercy of our ignorance about the true fundamental nature of physics to be able to calculate this. All we know is the value should be very large. So,
and it isn't by observation.
But it's not by observation, that's right.
Right.
And it turns out that in these different phases that I mentioned, it'll have different values, very different values. In some it'll be positive, in some it'll be negative. If you pick a phase at random, very likely it'll be extremely large, much larger than the observation. But if you have enough phases, then by coincidence, or not by coincidence, just if you have enough of them, there's going to be one or a few, or maybe many, but a small fraction of the total that have a small enough value that have the right value actually to be consistent with observation. And this is the best solution that anyone has ever found to this problem. Many people have tried, lots of theoretical physicists have tried to solve this problem over the decades. And in my opinion, this is the only plausible explanation. What's interesting is that if you ask how many phases do you need for this to work, the answer is about 10 to the 120. It's a 1 with 120 zeros after it.
How do you get to that number?
Because that's the degree of fine-tuning that's necessary. In other words, the observed value is 1 over that number of the natural value. So if you had that many phases and the vacuum energy is random, which is a bit of an assumption, but not a very strong one, actually. If it's not random, then there might be some other solution, because if it's not random, it means there's, like, for example, if it likes to be close to zero, then there's some other mechanism that could explain it.
So basically what you're telling me is that we measure a value of the cosmological constant, which is very surprisingly small compared to what our theories would naively predict, right?
That's right.
And so that's a puzzlement. I mean, why is it so small, right? And then people have tried to figure that out. And now you're saying that with the idea of the multiverse and having these different phases where this cosmological constant can have different numbers, if you have enough phases, there is going to be a non-zero probability that in some of those phases, it will be small enough, just like our universe. So our universe would be that phase where this number is small, by coincidence.
Right, and then you may ask, well, why do we live in a phase where it's so anomalously small? And the answer to that, as far as we understand, is that in phases where the vacuum energy is large, nobody's living. Right. Large vacuum energy prevents stars from forming, it prevents any kind of gravitational collapse, it blows all the structures in the universe into pieces just by tearing them to shreds and throwing the particles in different directions. It's a pretty violent force. It just expels everything. And so there's no time for any kind of life to evolve. There's no one in there in those phases asking the question, why am I in this phase? So it's called the anthropic principle. But really it just says you live where you can live.
Right, which to me sounds very tautological, but I have lots of reservations with the anthropic principle. I don't quite get it. But
I think it's the right answer to certain questions. And I don't think anyone would dispute that if you think about it. Like if you ask, why do we live on the surface of a rocky planet? If you think about all the places we could live in the universe, the fraction of the volume of the universe that's the surface of rocky planets is ridiculously small. It's not as ridiculously small as the observed value of the cosmological constant compared to but it's really, really small. So why don't we live out in outer space in between galaxies? And I think the answer is clear. There's nobody out there. So I think thought of like that, it's almost just, it is a bit tautological, but it means that it's not the right question to ask. You shouldn't be asking, why do we live on the surface of the rocky planet? The answer is obvious. That's the only place anybody can live. If there is this landscape, if there is a multiverse containing many different values of the cosmological constant, then it's exactly the same thing. Why do we live in a region with small lambda? Because of course nobody lives in these phases where everything is being torn to shreds.
And do you feel like that's a satisfactory explanation?
It's a satisfactory explanation for why we live on the surface of a rocky planet. So, I mean, we accept that answer because we understand very well the physics of planets and empty space and stars. We don't understand the physics of the cosmological constant very well. So in that sense, it's not satisfactory. We should understand it better. But if the understanding that we have so far is correct, then yeah, it's the only possible explanation.
Okay. And, you know, when I was starting working on this, during my PhD years, the idea of string theory and superstring theory was really, everybody was after the solution, right? The whole motivation was, we're going to have this theory and we're going to have the unique solution. And that unique solution will be awesome because it's going to have one constant, which is the string tension, you know. And out of the geometry of the internal space, we're going to compute everything else. So that was very compelling, right? Things have changed dramatically in the last 30 years or so, right? In the sense that you can't talk about the solution to string theory anymore. You're talking about many different solutions, right? One being this one, you know. And so some people may argue that, you know, when you have everything, you have nothing, meaning, you know, you have all these possibilities. So of course, something like us will come out of it. Does it really matter, you know? And that's a criticism that people have, right?
Right.
And on the other hand, there is this guy from England, Bernard Carr, who you probably know, who made a statement which is kind of provocative, which is, if you don't want God, you better have the multiverse. Which is basically about the initial condition problem, right? The issue that we, you know, why is it this way? Well, hey, the multiverse will tell you. You don't need a fine-tuner kind of cosmic DJ there to be doing this thing, right? So I wonder where you stand on this, you know, sort of more philosophical position. I mean, do you feel like, I mean, given what's going on with particle physics right now, with supersymmetry, having these issues with the LHC and stuff, and how do you feel in terms of the future of this field, you know, of particle physics and string theory in general?
Well, I think we've been fooling ourselves into thinking there should be a simple, elegant answer to these questions. I mean,
it's Platonic, it's beautiful,
exactly.
right?
I was just going to say, Plato had an idea that there are these Platonic solids, and so somehow everything had to be based on them. He even had this kind of theory of chemistry that you could combine two tetrahedra and form a cube or whatever. And I mean, you know, there was certain materials were made out of one kind of Platonic solid, other materials. And actually, that idea wasn't totally wrong. A lot of the principles of modern physics are rather similar to that in terms of symmetries and so forth. But if you'd asked Plato to predict, I don't know, how far away the sun was, the Earth was at the center, the sun was some distance away, the other planets maybe some other distance, he probably would have come up with an idea that it had something to do with Platonic solids. There were theories like this. People thought they could predict things like that.
Right.
Now
like
we
Kepler
know,
did.
Kepler,
Right.
but now we know that you can have planetary systems around stars with many different values of the radii of the orbits. You can have many different types of planets. The Earth is not at the center of the universe. Human beings are not unique. Our whole intellectual history has been a series of punctures to our perception of our self-importance, right? We thought we were at the center. We thought we knew the answers. We thought there was something special about what we knew so far. And no, it always turned out there was a huge other layer of complication that was way beyond what we could have imagined before. I don't see this as very different. I mean, we don't know it's true. It might not be. Maybe there is no multiverse. But to me, it's a natural extension of this chain of logic, that there should be much more than what we can see. And if there are all of these phases, then all of our efforts in undercovering the laws of physics, not to mention biology and chemistry, all of the progress we made in science is a tiny pinprick in the surface of this complexity that lies underneath it. There's this huge number of possible phases, and we're just looking at a little bit of the physics of one of those. So not only are we insignificant in the universe, our knowledge of physics is insignificant in all of the possible different versions of physics that one could have. So to me, this seems rather plausible, and it doesn't bother me in the slightest that there's no unique solution. I think it would be great. A theory with a unique solution to everything is the best possible theory because it's the most possible predictive theory and it's easiest to test and so forth. But it doesn't, I don't think we're close to that. Maybe it exists, but I don't think we're there yet.
So here's a harder question then. Let's say you don't find the signature in the microwave background in the next 10, 20, 30 years, whatever. At what point, and this is I don't think there is a very obvious answer. At what point do we say, okay, beautiful idea, didn't work, let's move on?
I don't think we need to wait that long, actually. I think we should always be exploring every possible alternative. Yeah. So, I mean, it's not that when I say that I find this to be the only plausible explanation, it doesn't mean that another better one won't come along. Right. It doesn't mean that I myself am not thinking about other explanations at the same time. I mean, the great thing about science is you don't have to believe in anything, and I don't really. I'm a skeptic at heart. So I don't believe any of this stuff in the sense of having faith in it. I just think that it's the best chance of the ideas that there are around. I think these have the best chance of being right, and that's why I'm working on them. Also, I think I can push them forward in a way that maybe I wouldn't be able to something else. So, yeah, we don't need to wait until we've looked and looked and looked and not found anything. We can look for other ideas right away. There just aren't any really good ones, at least not right now. Right. Yeah, we're all, as a community, we're all trying to find alternatives. And it would be great if we could explain the value of the cosmological constant. That would be a tremendous success. Not with this argument, but really calculate it and predict it. Right. That would certainly be superior to this. There's no question about that. It's just that there are very few things in the world that we can actually do that for. In fact, we can't calculate the masses of any of the fundamental particles. Right. We can't calculate any of these quantities from first principles. Right. And the things we can calculate are the results of tightly controlled simple experiments with ingredients that we understand very well. When we scatter two particles in an accelerator, we can predict the outcome, at least probabilistically, very accurately, because we understand the laws that govern those collisions very well, and we've measured the parameters that are necessary. We don't understand the cosmological constant at anything like that level. Right. So even if we knew what the ingredients were, for example, we can't use string theory to calculate the value of the vacuum energy in any of these phases that I mentioned. So to prove that there is one with the right value is way beyond what we can do. And this is just a technical problem. We don't have the mathematical skills to do it.
Yeah.
So,
well, it's a technical problem. But then you can also think, okay, let's backtrack a little bit and look at the fundamental constants, right? There are about 26, apart from the cosmological ones, just like in the standard model one, right? And those numbers, where'd they come from, right? They were just things that were measured in the laboratory, and you can even put in G in there. You can put the gravitational constant, right? And these are like, if you look how theories are constructed, right? I mean, historically, those numbers are sort of like aids, they appear because they need to be there, in a sense, to kind of fit things. So for example, when Newton came up with the gravitational force, he needed a constant in front that would, in a sense, regulate the intensity so that it would correspond to the observations. These are how the orbits go. Can't be too big, can't be too small. It has to be that number. And then Cavendish measures it. And then you can tell similar stories when Thomson measured, the charge of the electron, the mass, right, E over m, whatever. So there is something interesting going on here, which is somehow we are moving from this way of doing science where those constants appeared because they were necessary for us to construct an explanation of some phenomenon that we're measuring, E over m, g, the Planck's constant to fit the black body spectrum, to something that we want to calculate from first principles. It's just a very different thing. They're very different things, you know. Not saying that having the ambition is not a good thing. It's a wonderful thing, but they are different things.
They are. I think you could almost define success in science as reducing the number of those numbers.
Yeah.
And that has happened. I don't think this is purely a modern or contemporary phenomenon. I mean, for instance, if you think about the history of chemistry, I don't know much about it, but I mean, there's a periodic table which was at first at least painstakingly constructed by making measurements of the properties of elements, trying to decide what's an element and what's not, what's a compound. And I would think, I mean, the structure of the table, the way we see it now, was fixed by similar chemical properties, the way we have these columns and these rows and so on. And it only came, the understanding of why that is only came later, once the physics of of atoms was understood. So I think in that sense, I mean, if you have 100 elements and they all have different properties, you have a huge number of parameters that you're measuring. Now we can calculate a lot of those things because we know we have a more fundamental description with fewer parameters in it. So maybe something like that, I mean, I think that's what people are looking for. That was what string theory was hopefully going to be. And it might still be like that, but perhaps not for everything people expected out of it. So the cosmological constant in particular seems to be extremely difficult. It seems to not be one of the things that you're going to be able to predict easily, knowing the fundamental theory. But again, it's not going to stop us from looking for alternatives. And if we did have a theory that could predict it, that would be better. There's no question. That would certainly be better.
So, and last question. So how do you respond to people that say that the multiverse is just metaphysics, that even if you have a little signal on the microwave background, it's just a neighboring thing? You can't really go from that to saying that you have an enormous possibility, you know, of having all these other phases out there. And hence, it's not something that belongs to physics in a sense, because you can never falsify this thing.
When astronomers in the early 20th century were first observing other galaxies, there was a lot of debate over whether they were, in fact, very distant galaxies or whether they were some kind of nebula within our galaxy or things close to the solar system. I suppose you could have accused people who speculated that they were distant galaxies of engaging in metaphysics, because how are they going to prove that they're really distant galaxies? And what happened is more and more evidence accumulated. The theories that described them became more and more detailed and more plausible. The alternatives to those theories were ruled out by observations one after the other. Is that going to happen with the multiverse? Not in the near future.
Right.
But I don't think it's by any means impossible. I think specifically, one of the things that motivated me to do this work in the first place was precisely this sort of objection. It seemed to me that there was nothing fundamentally different about the multiverse than any other arena of science. It was just harder to make measurements. And I think what I've shown is that, at least if we're lucky, we could measure some of these parameters in the multiverse. We could see multiple bubble collisions. We could learn something about the phases inside those bubbles. That's about as scientific as it gets, I would say. Now, of course, again, it might be wrong. That's the nature of science. It always might be wrong. We might not see it because it's too faint, in which case we're simply out of luck. But it doesn't make the idea itself any more or less scientific. I mean, the idea that, so in my opinion, science should be falsifiable in principle. There should be experiments you can do which distinguish between your theory or one theory and a competing theory. That's more or less the definition of science. But they don't have to be easy to do. That would be a rather silly criterion to impose. I mean, almost certainly there are aspects to nature which are correct, but we cannot test because we don't have the technology. And if someone comes up with a theory of those aspects of nature 200 years from now, when we do have maybe the capability to test it, it's a scientific theory then, and it would be a scientific theory now. We just wouldn't be able to falsify it or confirm it very easily. Right. So, right. So I don't know. I think the idea that there's a big universe out there with a diversity of environments is so reasonable that it's strange that people would find it so objectionable.
No, I don't think they do. I mean, what kind of bothers people, I think, is the notion that if things are outside of our horizon, we just don't know how to access them. And And that's really the problem, right? That's what people talk about.
Let me make one analogy, if I could. Imagine you're an islander. So you live on an island, and you don't have any wood on the island. There's no trees, but you can grow crops. You have animals, fresh water, and your civilization has been living there for a long time, as long as anyone can remember. And you climb to the highest point on your island, and you look out, and all you can see is ocean, no other islands. And then time passes. You get more and more sophisticated. You can't build boats because there's no wood, so you can't explore. And the ocean's too rough to swim in, so you can't try to swim to another island. So as far as you know, there's nothing else. But you have some geologists who develop a theory of how the island formed. And they say, oh, there was a volcano on the ocean bottom, and it erupted and erupted, and eventually it formed this island. And a lot of people say, oh, this is crazy. Come on, how can you possibly know this? And they say, oh, look, we have some obsidian. We have these things that could only have formed in the volcano. It looks pretty reasonable to me. No, come on. And they say, well, if there was this volcano, there must be other volcanoes somewhere else in this ocean. And people say, oh, but you'll never test it because it's beyond our horizon. We climb to the highest point. We can't see anything. And then one day, some driftwood from a tree washes up on your island. And then you know there are other islands because there are no trees on yours. So beyond our horizon, it means it's too far away to see right now. It doesn't mean that some signal emitted long enough in the past couldn't have drifted across the space in between and eventually affected us. These bubble collisions are an example of that. They happen in the very early universe, but they can affect us now. We can see them. So if these theories are correct, not all of the multiverse, not all of these other universes are causally disconnected from us any more than those other islands are. They're just hard to see, and it takes some luck to know that they're there.
Yeah. I actually thought of one more question that we didn't really address, but we should, I guess, which is, you don't really need string theory for the multiverse. Just inflation, normal inflation will generate a multiverse. You know,
dark energy.
Yeah, so it's not really, I think that's an important point. That you don't need to go to 10 dimensions and supersymmetry and nothing like that.
That's right.
Right?
Yeah, we already know that the expansion, we know that the expansion of the universe now is accelerating. We have strong evidence that it underwent a period of much more rapid acceleration about 14 billion years ago, right after the Big Bang. And the essence of the multiverse, or at least one of the things that inevitably produces a multiverse, is accelerated expansion of the universe. That produces a universe that gets arbitrarily large rapidly. And even if there are no other phases of physics, there will be exotic possibilities that occur just because there's such a big volume and unlikely things will eventually happen. So even if there are no other phases in the sense I was describing, there's going to be other regions that are very different from where we live. And other phases are, again, something that you certainly don't need string theory for. You can have this, and you generically do have this in more conventional quantum field theories. So there are probably phases. There are almost certainly a very big universe. So again, it's hard to escape the conclusion that there's some version of the multiverse out there.